Hello, everyone, and welcome to the new Vishay webinar session. My name is Kathleen Hughes, and I'll act as moderator. The title of this webinar is SPICEification of Vishay of Linear Resistors with QSpice and the company QORVO. Yes, you heard it well. SPICEification is a new proper word for the description of Vishay non-linear products with QSpice from our company QORVO. First, let me say some words about today's presenters. Josh Polema is product manager at Vishay for nonlinear resistors. He's based in Columbus, Nebraska. Josh is going to make the general introduction of nonlinear resistors. He will briefly be followed by Alan Stas, product marketing engineer with the same product family. Alan is based in Brussels, Belgium. Alan is very busy with SPICE simulations now for more than 10 years. Thus, Alan will proceed with the presentation of our main topic of the day, SPICEification of the products with the software QSpice from QORVO. After that, we'll have some time for a Q&A session. Do not forget to input your questions during the presentation. Write them into the questions pane, and we're going to proceed now, and I'll give the word to Josh. So Josh, the floor is yours.
Backed by popular demand, the topic of electronic simulation will once again be featured today and provides as a supplement to last year's webinar, Solutions Unleashed, Exploring Electronic Simulation with Nonlinear Resistors for Temperature Sensing and Circuit Protection, linked here for your reference. At the end of last year's webinar, we made a poll to our listeners about the need for other software explorations with a focus on Vishay products. Seeing the positive feedback from FPGA engineers and firmware engineers alike, that were present during the webinar, we are now ready with two new software platforms for showcasing the capability of our products through simulation. The first one, as was presented in the title, QSpice, from the company QORVO, will be highlighted today. QSpice is a brand new software which can perform all the simulations we shared on the previous webinar and much more. As Alan will show you later, QSpice is ideal to simulate digital temperature control, which is somewhat new. I will not spoil what's to come, but there might be a pleasant surprise in Alan's presentation later on. For those of the audience who are not aware of the Vishay Nonlinear Resistor portfolio, let me make a summary of our product ranges with a special emphasis on those product families that will be highlighted in the simulations performed by Alan. I will begin by providing a high-level overview of Vishay's nonlinear resistor product portfolio, which is comprised of a broad range of component options for design engineers to consider when temperature sensing, compensation, and electrical protection circuits are needed. NTC thermistors and RTDs are a perfect fit for temperature measurement and compensation, while PTC thermistors and varistors are commonly used in circuit protection applications. Within each product classification are a variety of electrical options as well as different packaging selections, ranging from wired to surface mount to housed assemblies. The options are abundant, including Vishay's ability to customize to meet the unique requirements of a given design. In today's webinar, Alan will showcase three distinct product families using innovative QSpice models to simulate product behavior and performance in numerous application examples. You will get to see our NTCS family in action in a few different temperature control applications. The NTCS is a surface mount component with wraparound terminations that is primarily used for monitoring temperature on rigid or flex PCBs. Several end-use applications can be considered when evaluating the NTCS component family. Some common applications are outlined here. Next, the PTC EL67 product family, a brand new release from Vishay, will also be put on display for limiting inrush current in a battery pre-charge circuit that is commonly found in electric vehicles. The PTC EL67 is a high energy absorbing ceramic PTC which can be used to reduce component count as compared to the standard line. It also boasts the key advantage of self-protecting in case of overload with no risk of overheating. Typical applications where PTC EL67 can be used are shown here. Finally, the most popular housed assembly from the Vishay lineup, the NTCA Lug series, will be simulated in a surface temperature sensing environment and will highlight the ability to correlate between electrical and thermal systems in QSpice. The NTC lugs are remote surface temperature sensors offering a high electrical insulation in combination with excellent thermal conductivity and stability through a screw mount design. Some of the many potential applications for use can be seen here. For a more detailed look at the entire Vishay nonlinear product portfolio, feel free to navigate to last year's webinar introduction or visit Vishay.com. To close out the introduction, it must be noted that any nonlinear resistor component from Vishay can be SPICEified using QSpice models, making it now easier than ever to build Vishay into your design. The message here is, do not hesitate to reach out to us. You can find us at edesign.ntc@vishay.com. Please send any questions or comments regarding electronic simulation. As a reminder, there will be a Q&A session at the conclusion of this presentation, so be sure to have your questions ready for live interaction, or alternatively, you can enter them into the chat at any time. Now, on to the portion of the show you've all been waiting for, using QSpice to unleash solutions that will revolutionize your designs. Alon, take it away.
Well, thanks, Josh. I am thrilled and honored today to be able to air a kind message recorded for us at APEC 2024 by Mike Engelhardt and Jeff Trank from QORVO. After that, I will directly start the QSpice session. So, here is the message.
Hi, I'm Mike Engelhardt from QORVO. Thank you, Alan Stoss. I'm happy Vishay is moving forward with adopting QSpice. Please feel free to reach out to me if you need any help.
We're thrilled that Vishay is using our QSpice simulation engine to highlight the performance advantages that their products bring to the market. QSpice is our contribution to the power electronics community. It's free for everyone to use. We've got a fantastic forum at forum.qorvo.com where you can join the conversation. Thanks and enjoy the webinar.
QSpice from the company QORVO appeared in the first half of 2023. One of the important points I would like to emphasize here is that QSpice supports VERILOG and C++. So, the same way you import your SPICE netlist into the software, you can describe digital electronics with circuit blocks and interface them with the analog sensing parts and the control parts of the circuit. Such feature is thus the missing link between the SPICE of yesterday and the SPICE of tomorrow. The first example of temperature control circuit that we are going to simulate with QSpice is this simple on-off control circuit using an RS latch with a new feature of safety threshold preventing the circuit to heat indefinitely in case of sensor in open circuit. Let me just briefly describe the circuit before simulation. We have an oven modeled with a thermal RC circuit. It is heated by the current passing through R4, which is commanded by Q1. The oven temperature is measured by a thermistor whose signal is compared to three voltages: a low value for the fixing of the high temperature, an intermediate value for the low temperature, and the highest value for the failsafe in case of open circuit. The gray box here is the VERILOG RS latch, which commands the heating part of the circuit. Right-clicking on this box opens a menu where you can visualize the VERILOG coding. Here, a very simple one. Let's wait no longer for simulating the circuit. The initial oven temperature has been fixed at -40°C on purpose, so that we see what's happening when the thermistor voltage is higher than the failsafe threshold. So we see at the beginning that there is no heating. The oven goes slowly back to ambient temperature. Once it has reached the temperature fixed by the failsafe voltage, heating takes place and the steady state temperature will then swing between the two maximum and minimum temperature thresholds. If the ambient temperature outside of the oven decreases down to -40°C, the heating losses will increase, and we see that the heating cycle is becoming longer. QSpice allows, of course, the user to sweep the NTC thermistor parameters in tolerances on R25 and B value. The simulation result will provide a bundle of curves showing the limit cases. The second example of an application based on a VERILOG module represents a pulse width modulation of a Vishay VOT8125 optotriac triggering itself another triac. This last triac is commuting an AC main voltage onto a load, which produces the current used to heat an oven. The oven temperature is measured by an NTC thermistor NTCS0603E3-103JLT with some response times delay fixed by the couple R11C2. The oven temperature-depending voltage generated by the thermistor is converted by an ADC internal to the controller, while a sawtooth signal is produced by a simple counter to generate the pulse width modulation signal. All of this is included in the VERILOG module. Let's start the simulation. When the output of the controller is low, the optotriac is switched on and the heating is also on. At the startup of the heating, the duty cycle will be high, and as we approach a steady state, it will be low. The temperature of the oven increases from the initial ambient temperature to the steady state temperature fixed by R7, in this case 6000 ohms, corresponding to a set temperature of about 43 degrees C. 4 extreme cases are represented here and depend upon the thermistor tolerances. The third example now. We go crescendo into the complexity of the design, and here, in this application, we deal with a thermoelectric Peltier element used here to stabilize in temperature a heat source which produces periodic peaks of several watts. And this in an environment where the ambient temperature can rise up to 45 degrees C. The Peltier element uses a current driven by a MOSFET whose gate is driven by a controller. This controller will use the information of the temperature measured by an NTC thermistor. It will compare it to a threshold given by a reference voltage. In this case, this voltage is given by a virtual thermistor placed at the reference temperature 25 degrees C, which is the temperature to be kept. We come now to our VERILOG coded controller, which needs to contain all the digital hardware to produce pulse width modulation for the gate of the MOSFET. Right-clicking on the controller gray box and opening the VERILOG code makes the code visible. We will see later how to validate this coding. Let's now run the simulation and verify that the pulse width modulation of the current passing through the Peltier succeeds in keeping the cold zone of this element around 25 degrees C despite the power pulses and the ambient temperature variation. The upper pane shows the PWM current through the Peltier and the power pulses by the heat source in red. The lower pane shows the different temperature of the system. In red, the ambient temperature, in blue, the temperature of the cold zone, and in green, the temperature of the hot zone. On the mid pane, you see the offset between the cold zone temperature and 25 degrees C. This offset must remain as low as possible. We can see how each power pulse induces a small positive temperature increase, immediately followed by a cooling by the PWM. Also, the huge ambient temperature change by more than 15 degrees C increases the cold zone temperature by a few tenths of degrees C. The pulse width modulation duty cycle is changing depending upon the variation of the ambient temperature. We see that when the ambient is at the maximal value, the duty cycle of the PWM is also maximal. So the circuit works really as intended. The temperature of the cold zone is remaining within more or less 0.3 degrees C from the target temperature 25 degrees C. All the parameters can be adapted to your own application. The Peltier characteristics, the capacity of the cold and the hot zone, the power of the heat source, as well as the ambient temperature variation. We come now to a fourth application of temperature sensing and control, and in this one I have reproduced a PID controller under the form of a digital VERILOG block. I use a Wheatstone bridge with a thermistor NTCS0603 and some fixed resistor TNPW. Note that right-clicking on all the circuit elements opens a menu where you can directly order the parts at an official distributor. We still have a modeled oven whose temperature is measured by an NTC. An error signal is provided by the Wheatstone bridge by comparing the measured temperature to the target profile. And this error signal is then treated by the PID controller with a proportional, a differential, and an integral contribution. Let's now examine a bit closer the coding behind the PID controller. Now we know the routine. Right-click, Verilog interface, open Verilog source. When you write your Verilog code, if you want to verify if your code can be compiled, right-click on the code. A menu proposes you to compile Verilog to C++. Click on this and you will have your code verilated successfully or not. And if yes, a .dll is created. We can do this for any of the blocks, and if your code can be compiled, you're good to go. And you can run now the simulation. We are going to follow the oven temperature, the set temperature, and the ambient temperature beneath on the lower pane. On the higher pane, we visualize the voltage offset of the Wheatstone bridge that the PID tries to maintain to 0. The second pane starting from above is in fact the control voltage applied to the QORVO MOSFET gate. And the second pane starting from below is the temperature accuracy which must be maintained to 0 as much as possible. We can add as well the heating current above all these panes. At the first temperature dwell, the PID reacts in a good way. There is no temperature oscillation, only a smooth small level transition. And as the PID coefficients have already been optimized with QSpice, the fitting to the profile will be optimal until the end of the cycle. Right, I have now fast forwarded the simulation to the end, and we see effectively that the offset between the measured temperature and the set profile is really kept to a minimum between minus 0.4 degrees C up to 0.2 degrees C, taking account of the transition periods. This is for a nominal thermistor. We can now test the thermistor tolerances. For example, let's say plus or minus 1% on R25 and plus or minus 1% on the B value. We can also add tolerances on the fixed resistor, the TNPW. Let's disactivate the SPICE directives related to these different tolerances. Doing this, I remark that QSpice is a software which allows 4 simultaneous sweeps in the same simulation, and this is remarkable enough to be pointed out. We performed a worst case scenario. The thermistors R25 and B and the tolerance of the TNPW take their minimum and maximum value. We have the 16 run cases, and when the result is available, we conclude that the temperature control will be overall just above plus or minus 2 degrees C. Moving now to another application than temperature control, and this time involving Vishay PTCs, the inrush current limiters. I would like to point out that we have models of this component in QSpice as well. Here is a simulation of a circuit commonly found in battery precharge circuits in electric vehicles. A sinusoidal voltage is rectified and used to charge a capacitor with a network of PTCs whose function is to limit current and switch in open circuit in case of overheating. I have exposed such kind of simulation in a preceding webinar about nonlinear resistors, and QSpice is also up to the task to simulate it as well. Some models of PTCel67 can be found, as always, at the website hackster.io. Let's simulate the charge of the capacitor, and let's record the voltage rising on this component depending upon the PTC R25 tolerance, the ambient temperature, and the value of the capacitor. When the simulation is over, you will be able, with the help of some SPICE directive, to compute the charging time depending upon the R25 tolerance and also the ambient temperature. The last simulation I will show in this webinar is the reproduction of the thermal behavior of one of the Vishay most popular sensor assemblies, NTC-ALUX01T. When such component is cooled on a metal plate and submitted to a temperature step, the response time is as follows: an S-shaped curve with a gradient between the plate and the lug at the steady state. QSpice allows here to quantify very accurately the Laplace function representing the thermal Foster model of the component. Sweeping 5 time constants leads thus to value optimization of the response fitting. With the optimal final values of the time constant, we can reproduce the thermal response with a very good accuracy. This example shows that we can solve the thermal function question with the SPICE software thanks to the analogy between thermal and electrical systems.
Fantastic. Well, we're going to open it up for Q&A now. Just be aware that you can continue to type your questions into the questions pane in your control panel. So right now we do have one good question that just came in. Well, in all the digital temperature sensing simulations, the same component was used. Is there any particular reason for that? Is there a QSpice model available for other components as well?
Yeah, I can take that one, Alon. So yeah, it's a great question. So each and every NTC can in fact be SPICeified, as we've coined the phrase now. All that needs to be done is updating the net list with the Steinhardt and Hart and the dissipation coefficients. That will be all that's necessary to implement those. The main reason for the 0603 10K product being chosen for several of the simulations shown today is really because it's the most standard in the market, and it does offer a very good sensitivity across the entire temperature range. And just to give a plug for future development, we're also working on a version of this product that will become ROHS compliant with no exemptions, and also keeping resistance to temperature stability up to 180 degrees C. So the SPICE model will not change for that. So putting this particular product into your design should future-proof the design, and you'll be set for the future applications that you're working on. So that's the answer to that one. Hopefully that was helpful.
I suppose so, Josh. So I see another question. Will there be QSpice models of nonlinear resistors soon available on the Vishay website? Well, right now, not yet. You have to go to hackster.io, which is the technical blog of Avnet Farnell element 14, and look for the QSpice simulation with Vishay components. And you will find there some simulation. And if you use other components that those tested in the simulation, feel free to address your question to edesign.ntc@vishay.com, and you will certainly get your model very soon. For the PTC, the new QSpice simulation involving PTCel models are so fast and effective compared to what we have published until now that we are soon going to put this model and simulation on the Vishay website together with new product PTCs, the SMD version, which are going to be introduced very soon. Right, let me check if we have any question. Yeah, there is. Sorry.
Okay,
Yeah.
I can jump in
So
here and help. I
Yeah,
can jump in here and help. So the next question is, they had trouble signing into the GT webinar's TLS security requirements. They missed the first 10 minutes of today's webinar, so they're wondering if a recording is going to be available for them after the webinar today.
yeah, for sure. So this webinar has been recorded, and we are going like the last one to. The recording will be available to anyone. I think it will be on the Vishay website and also on YouTube, just like the first webinar, Josh. I think
yeah,
it's on YouTube. On
yeah,
YouTube, huh?
that's correct. And also, Alon, maybe you can give a quick mention of the document that you created, right, with all the SPICE models. This is because it does say supporting documentation. So we do have a document that really outlines every Vishay product from the nonlinear resistor portfolio with a number of different applications. I don't know if there's anything you want to add to that, Alon, or we can find that.
There are some specifically to QSpice. Right now, you need to go to hackstore.io, and then you will get that a lot of simulations, or principally all the simulation which were displayed into the webinar. They are there for downloading, so the people can download them freely, and you will find some documentation, some list, everything that you need to do to make such kind of simulation, and including the libraries and so on. So now the motto is go to hackstore.io and select the simulation which are flagged by Vishay and QSpice. I think there are 8 simulations already published. So these are the documents that we that are published at the moment.
Perfect.
Right, and if you don't find the component, the net list of the component which are of your interest, you can always ask it to the address dedicated to the SPICE simulation by Vishay, adesign.ntc@vishay.com. We answer very, very quickly. I don't know if it is answer to you. All right, thank you very much. So I got the message that it was sufficient. Next question was, yeah, there is a question, of course. During the preceding webinar, we have presented a lot of simulation with a lot of EDA. What's the point now of QSpice about all these EDA? But in fact, we as Vishay, we are component manufacturer, and our intention is to publish as many models as possible in all EDA which are available, and we consider that the user are up to the task to decide for themselves which is the best for them. I think that if you listen to the preceding webinar, it was quite obvious which EDA was a favorite. And now for the future, try everything that's new, like QSpice, especially if it is free, because when you have to pay, there is no money back. And compare the result of the simulation to your practical result. Just see how fast you can have some results and decide for yourself which EDA is the best, right? I think there is still a question. Yeah. It was mentioned by Josh that we have two new EDAs since the last webinar, and the first one is QSpice. The second one is it was mentioned about MATLAB. So when will the session about MATLAB will happen? It's already ready. It's also in collaboration with the MathWorks. So I can suppose that we will air it in October or something around this period. Right? So I don't see any further questions. So it's time to thank everybody, and I would like to take this occasion to particularly thank Mr. Mike Engelhardt, Jeff Strang, Surinder Singh from the company QORVO, because they helped a lot to make this webinar possible with their cooperation. And as you can see here, I'm also very glad to have received a shirt from the APEC which represent the creator of QSpice, Mr. Engelhardt. So thanks a lot to them. And for all the listener, speak to you soon for a new session of simulation with Vishay Non-Linear Resistors, NTC and PTC thermistor and RTD. So thanks a lot, everybody.
I think you need to take that T-shirt and put it on your website and sell it, because I would buy one. That is awesome. All right.
I don't know if it's still available from QORVO.
Josh, do you have any closing words before I sign out for us today?
No, just thanks to everyone for attending, and as Alain said, we'll see you soon on the next webinar with MATLAB.
Fantastic. All right, everyone. Thank you so much for joining our SPICEification of Vishay. We really appreciate your time, and have a great rest of your day.
All right.
Thank you. Bye.
Thank you. Bye.